Hey everyone, it's me, Miss B, and on today's video, we're looking at the Unit 4, Lesson 8, Cumulative Practice Problems for Illustrative Math Geometry. So this one was all about sine and cosine and how those two are related when we have angles in the same triangle. And so, as you know by now, we don't do the sine or cosine on the 90-degree angle ever, because it's about the relationship between the sides from the perspective of the acute angles. And acute just means less than 90. So one of the key ideas from this lesson, and I'm going to write it here at the top, is that basically if we have the sine of one angle in a triangle, one of the acute angles, that's going to be equal to the cosine of the other acute angle. So if we had the sine of theta, that's going to be equal to the cosine of 90 minus theta, because whatever that many degrees is, we would subtract it from 90 to find the other angle. Also, likewise, if we have the cosine of theta, that would be the same as the sine of 90 minus theta. So it works both directions, whichever angle you start with and whichever term you start with there. So that's our main idea. We're going to go through and answer some questions now. So for question 1, they want us to select all the true equations. So this first one here says cosine of 15 is equal to sine of 15, and I know that is not true, because one is opposite over hypotenuse and the other one is adjacent over hypotenuse. Now it says cosine of 75 is equal to sine of 15, and because 75 plus 15 is 90, then this is true because it fits with our pattern on the right. The cosine of 75 is equal to the sine of 90 minus 75, which gives you 15. So option C now has the angles flip-flopped, but it's still saying cosine of the same thing. That's not true. Cosine of 75 is not going to be the same as cosine of 15. For D is also going to be correct here because cosine and sine, so we're using two different trig functions, and then the 15 and the 75, 15 and 75 makes 90, so this one works, and it's cosine and sine. And then we did not learn anything about the relationship between tangent, but that one is not true. Okay, so that brings us to question 2. We're going to write two expressions that can be used to find the value of x. Now, we want to use an actual expression that doesn't involve the y over here, because we want to actually be able to solve it and use it to find x. And if we don't know y, then we can't find x. So we're not going to include tangent because tangent would be opposite and adjacent, the two legs. And so we can't use tangent. We have to use something that involves x and the hypotenuse. So let's write this one out as, I'll start with the 25-degree angle. So in that case, from the 25, since that's here, x is the adjacent and 11 is the hypotenuse. Adjacent and hypotenuse means I should be using cosine. So the cosine of 25 degrees is going to equal adjacent over hypotenuse, so x over 11, which means if I multiply both sides by 11, the denominator there will cancel. We'll be left with x, and then over here we'll have 11 cosine 25. And so that is our first expression that we can use to find the value of x. Now technically we can write, we can use x in part of this and have the equation, but they just wanted the full expression like solved instead of just writing out cosine 25 equals x over 11. They wanted us to do the work so that it's like solved for x. So if we write this out the other direction, again, I can't use y, so I have to still use x and 11, Normally with the 25, the only way we'd be able to do that is with cosine. However, we do know that we can use sine. So we're going to use sine and use the 65. So we're going to be able to say sine of 65 would give us that same relationship of x over 11 because the sine of 65 is opposite over hypotenuse, so x over 11 still, which means that our expression here, we're going to do the same work. We're going to multiply both sides by 11. It's just going to be 11 times the sine of 65. So these are our two separate expressions. Maybe I'll move this just so it's not in the way of my other question. I might move this like over here. Scoot it up a little bit, move some of this stuff around, sorry. So scoot you up just a tad. There we go. That way you can still see them, but I'm going to need this diagram for my other question over here, which is question number 3. So Andre and Mai are discussing how to solve for side AB. So let's indicate side AB. AB is AB, so they also have it labeled here as x. Andre thinks he can use the equation tangent of 12 equals x over 6 to solve for AB, and Mai thinks she can use the equation tangent of 78 equals 6 over x to solve for AB. Do you agree with either of them, and show or explain your reasoning? So even though the lesson itself doesn't really go into the use of tangent, we do talk about in the lesson that the angles that are complementary to each other here, when we switch from one to the other, the opposite and adjacent change. So that should affect tangent. It just doesn't affect it the way that it gave you as an option in the first question. So let's investigate. I'm going to use a red color for Mai's equation, and I'll use a blue color. I'm sorry, red color was for Andre, and the blue color was for Mai. So the red is that the tangent of 12 is x over 6. So Mai is using this one. Sorry, I keep saying that. It's Andre. Andre's using this one and saying that this is then going to be opposite, and the 6 is going to be the adjacent. So yes, I would say that tangent of 12 should be x over 6, because that does give us opposite over adjacent. And when we have SOHCAHTOA, tangent is opposite over adjacent for TOA. Now let's look at Mai's equation. She's saying the tangent of 78. And that 78 that she's using initially is down here in this corner, 78. 78 and 12, when you add them up, make 90. So let's just write that here, 78 plus 12 equals 90, so that we're, you can understand a little bit what I'm going for. So when we write out this one, the opposite from 78 is actually the 6. So this is the opposite. And the adjacent is the one right next to it. That is here the x, so it is the adjacent. Now, tangent is opposite over adjacent. So according to Mai, we would have tangent of that larger angle, so the 78. And that should be equal to 6 over x. That checks out, and Andre's equation checks out. So I'm going to write a little sentence here and say, I agree with both. Because when we switch acute angles, you know what, let me word this better. When we switch to the other acute angle, because the way I was phrasing it originally is going to sound like we switched the places of the angles, but that's not true. We're switching to the other acute angle in the triangle. The opposite and adjacent sides change. So that's how both of theirs can be correct, because 78 is the other acute angle. And that's all for question 3. That means we're going to move on to the back of this page. So here we have Jada visiting New York City to see the Empire State Building. She is 100 feet away when she spots it, and to see the top, she has to look up at an angle of 86.1 degrees. So how tall is the Empire State Building? First, we're going to draw a picture. 100 feet in comparison to the height of a very tall building is not very much. So if I have Jada, we'll draw a little picture here in blue. So if I have Jada standing here, she is obviously not going to be to scale. Her view is, she's not going to be very far from it. But the Empire State Building is going to be really, really, really tall. Now, it's difficult here to make an actual to scale, because I'm sure it is much different from that, but you have an idea of like the tall side is the building. So I'm going to call this X, and they told us she was 100 feet away. Now, they also told us that the angle she has to look up at is 86.1. I'm just going to label it in here, 86.1, so you can see, because it was a little too hard for me to write in that small area. So that's a picture. Now, if you wanted to draw this bigger, you could take it over here and draw your picture larger in the side where there's some space. I'm not going to do that. I'm going to leave it there. But now we're going to set up an equation and solve for the height. So that 86.1, since we have pieces here that are now opposite from where Jada is standing, and then adjacent, that means we're going to use tangent. So I would say tangent of her angle of 86.1 is going to be equal to x over 100. That means we'll multiply by 100 on both sides. And then we will just be left with x being 100 times the tangent of 86.1. And this is where we would then plug it into a calculator. So I'm going to grab a scientific calculator and plug that in so I can give you an estimate. I may have to round it a little bit, but I will give you an approximate answer in decimals. So 100 times tangent of 86.1. Calculator says that is 1,466 points. Well, it says 0.852922. So let's round that. I'm going to say 853 since it was 8529. So 8, 5, and the 2 gets rounded up to 3 because of the 9 that came after it. So this is my calculated height. That brings us to question 5, and then we only have 6 and 7 after that, so we're getting closer to the end here. Find the missing measurements in triangle ABC, and they gave us a triangle with a 35-degree angle over here, and then a side that is 9. So first off, I think the easiest thing to find is probably the degrees, because the angle measurement for The angle measurement for B, sorry, my cat is got the zoomies right now, and he's doing some pretty crazy stuff, so that's why I'm chuckling a bit. So the measurement of angle B is going to be whatever would add with the 35 to make 90. So I'm going to say 90 minus 35 will give us what that should be. And so that measurement, I believe, is 55. So 55 degrees for measurement of angle B. That's um, our first missing piece that we found. So we'll just put the 55 in here too. 55, great. Okay, now we need to find our two missing sides. I'm still going to use the 35 for my sine, cosine, and tangent, so I'm still going to use that as my perspective. So I'll highlight this one, I guess. I'm going to use this angle right here of the 35 degrees, just so that, that's the one they gave me, because you never know, I might have made a mistake in subtracting. I always like to go with what's labeled, especially if it's a whole number, and my answer to my other pieces are decimals, because sometimes that will happen. So let's label then. I want to say, I'll call this one X and this one Y. You can use whatever variables you like. You could also just refer to them as AB and AC. Both of those would work fine. So we're just going to call them X and Y. I like single variable names a little better, but as long as you label them, you should be fine. So X and Y, and then let's set up, we'll solve for X first. So X is going to be opposite from the 35, Y is going to be the adjacent, and 9 is the hypotenuse. We can tell which one is adjacent because adjacent will always be part of the two lines or one of the two lines that create the angle there. Opposite will never ever touch the actual point that we're using for the vertex of the angle. So let's set this up here. So I'm going to try to do my work in different colors here so it doesn't blend together and it's easier to see. So if we have opposite and the hypotenuse, that's where we're going to start first. So I can't use these two together. It doesn't work that way. I need to use 9 and X. So we're going to say that sine, because that is opposite over hypotenuse, so sine of 35 is X over 9. And so X is going to be 9 times the sine of 35, which means I'm going to plug that in my calculator here. Nine times sine of 35. That is 5.162. And this is technically slightly rounded, so I'm going to say my wiggly approximate 9.562. Okay, so I'm going to put a box around this. This is a missing side length. That was AB. And now I guess I'll do my other piece here in black. We're going to use the adjacent and hypotenuse, so we're going to use the cosine of 35. And that's going to be equal to y over 9. So we're going to have that y is equal to 9 times the cosine of 35. And so that means that y is equal to cosine 35, 7.372. Oh, and I did just say I was going to use a little wiggly equal sign because technically I'm rounding my answer a little bit. And then I just went and didn't do that. So I'm going to fix that. So those are my 3 missing pieces. That means we're done with question 5. Let's move on to question 6. Right triangle ABC is shown. We want to write 2 expressions that are equal to the length of side BC. So I can do two things here. They're only giving me the 55. I could use some subtraction and find the 35. Um, I could also, since I have two sides, I could use the Pythagorean theorem. So if we're using the Pythagorean theorem, this side here would be C, and then we would consider the side opposite from the vertex A to be little a, and the side opposite from vertex B to be little b. So I could say that a squared, which is BC, plus 4.9 squared equals 6 squared. And so I can multiply these things out to solve it. I'm actually just going to leave them in their formats here without squaring these pieces. So I'm going to say a squared, but I'm going to subtract 4.9 squared from both sides. So we'll end up with 6 squared minus 4.9 squared. And then we would have to take the square root of both sides. So I could say a is then equal to the square root of 6 squared minus 4.9 squared. I'm only leaving my answer like this because they wanted an expression. They didn't want me to actually write out what the answer is. But I believe we can use the other angle and what we know about sine and cosine to swap some things around here. But I like using the Pythagorean theorem too, so I just felt like showing that one. Let's use our 55 degrees, and with the 55, we have the one across from it, so the opposite, and then we have the hypotenuse. That's O and H, which means we have sine to make the SO part of SOHCAHTOA. So we would say that the sine of 55 is going to be equal to 4.9 over, oh, that's 4.9 over 6. I am so sorry. I already have all of that. That's not going to make sense. It should be equal to 4.9 over 6, but I want to find A. I want to find the piece that's missing. That's my adjacent. So rewind. We're going to do cosine of 55, and that's going to be equal to A over 6. So I can also say that A is equal to 6 times the cosine of 55. And that is an expression that is equal to the side length of BC, same as this one. We can even go a little further if we really, really want to. And we can use what we know from today's lesson, even though this is not supposed to be from today's lesson, but we can use what we know from today's lesson, go one step further and say that we know that the sine of the opposite angle should give us that same ratio. So sine, we're going to figure out what our opposite angle is, but that should still give us A over 6. And so 90 minus 55, I believe, gives us 35. So we could say sine of 35 gives us A over 6. So A would then be 6 times the cosine of, oh wow, I'm writing cosine because I'm looking at the one above it. 6 times the sine of 35. Yikes, making mistakes today. If I make mistakes while I'm solving, I tend to leave them in the video as long as I catch it while I'm doing it. But sometimes I make a mistake and I like finish the problem and then I catch it and I have to go back and edit the video together. But just so you guys can, and I even made another mistake here. Come on, Miss Bauman, what are we doing? What are we doing here? This is 35. My brain is all over the place. Sine of 35. So if you caught that one, good job. If you caught it before I caught it. 6 times sine of 35. So I technically have 3 pieces here that we could use. These are all of the variety of them. I'm not solving them out for actual numbers because they wanted two expressions. So I am leaving them as expressions, which are not solved yet. Okay, last question. Maybe I won't make 3 mistakes in a row on this one. Or maybe I will. Maybe it's just that kind of day for me. We'll see. So a triangle has side lengths of 7, 24, and 25. We want to verify that this is a Pythagorean triple. So in order to verify that something is a Pythagorean triple, you substitute all of those numbers into the Pythagorean theorem and show that both sides are equal. So in this case, we would have A and C. Now, A and B, you could swap. Like, this is fine. If we flip-flopped these, that's okay. But it's going to be equal to, and then the C is going to be on its own. So we need to square all of these. So 7 squared plus 24 squared is going to equal 25 squared. And we're just going to multiply all this out. Off the top of my head, I don't know what 24 squared is. So we're going to put that one in a calculator, but I do know 7 squared is 49. So 24 squared is 576. And I believe that 25 squared is 625, but I'm still going to check that one because I'm not positive. It is 625. So now we're just going to verify that 49 plus 576 is 625. So 625 is equal to 625. Both sides are balanced. We have verified it. Okay, now the next part is to approximate the acute angles. This says approximate, not use sine, cosine, and tangent to find them exactly. So through approximation, we are going to use our table of values. So I'm going to bring up my picture thing here and shrink it down to a decent size so that we can use it. Okay, so I'm going to leave it right there, and then we'll highlight some stuff from this. So I'm going to also just draw myself a reference here because I have a hard time imagining these things without actually having a triangle to reference. So it's not going to be to scale, but this would be like 7, 24, 25. So if I was to approximate the acute angles, we'll start with whichever one is next to the 7. That's probably going to be the larger angle. So I'll start over here and call this like theta. And then we know the other end is going to be 90 minus theta, but we'll start with verifying theta. So we would be looking for, from this perspective, this would be our opposite, this would be our adjacent, and this is our hypotenuse. So since adjacent over hypotenuse is in the first column, it's closest to the degrees, and I like to use that if I can to verify these things here. So if we're looking at our adjacent over our hypotenuse, we are going to look at what is the value of 7 over 25. I'm going to plug that in a calculator. Round it to, I actually don't need to round it because it does not go on forever. So this is 0.28. I was going to say round it to 3 digits, but it's a set number. So we're going to now look for 0.28 in this column. And I did say that it would be probably a pretty big angle because this is the shorter leg, so it's going to be closer in here, which means we're going to have a bigger angle the further we have to like look up towards the top of that building. So yeah, it does actually fall here between these pieces. So if I'm saying 0.28, that is definitely going to fall between these two values here, which means it's going to be between 70 and 80 degrees. Is that going to be halfway in between? Let's check this out. Minus 0.1. Oh, you know what? Let's take the average of those. I'm just going to do some quick math here to help me. Technically, if you gave an answer that's between 70 and 80 degrees, at least in my class, I would be okay with that answer because you are approximating. I like to be a little more specific if I can, so I'm going to try to actually estimate. So I'm just gonna, I can actually narrate what I'm doing on my calculator here. I'm adding them together and dividing by 2 to find the average because that should be halfway in between. So when I divide that by 2, I get 0.258 is the halfway mark. So if this is evenly spread, 258 would be like 75 degrees. This is a little bigger than that. So you'll notice that if our cosine is bigger, the top one here is bigger. That's the smaller angle. So we're going to just do this closer to 70. I would maybe say this is like 74. So it's going to be pretty close. 73, 74. So I would say, I'm going to say theta is approximately, well, actually, I should label this one here. 7 over 25 is the cosine of theta is equal to that, which is that. So I can say now theta is approximately 70, I'll say 74 degrees, which means I think they gave you beta on another question. So I'm going to say that beta is going to be equal to 90 minus theta, and 90 minus 74 is 16. So that'll be my approximation of that one. So I would say 74 and 16 degrees. And again, as long as your numbers are in between 70 and 80 for the larger angle, and then the smaller one is then going to be in between 10 and 20, and as long as they add up to 90, you should be good. So that's all for this homework assignment. Hopefully watching this helped you with some of these questions. And yeah, this has been the Unit 4, Lesson 8 Cumulative Practice Problems for Illustrative Math Geometry.